All right, recording is rolling. Welcome to Thursday, September 28th. I have an FRQ lined up for you guys. You probably have it on your desk. This could be one of the long FRQs. When you guys get the AP exam in May, you guys are going to get 5 FRQs, these free response questions. 3 of them are going to be short 7-pointers. 2 of them are going to be these long 12-pointers. So yeah, you guys got one of the big ones today. You guys remember your chapter 4 puzzles are due tomorrow. We've covered them all in class, so some of you guys have already turned those in. Then your take-home quiz is due on Monday. Oh, and what are you guys going to bring tomorrow? Laptop. Right, we're going to knock out this CR for CR test. Right. So before we get to this type of stuff, what I was hoping I'd be able to fit in class, but wasn't quite. Here, let me show you guys what I'm doing with my honor students, because this is pretty cool. Okay. Suppose you have this problem where you're trying to build a factory. You're trying to figure out what's an optimal location for the factory based on transportation costs. So suppose maybe we're like making pencils, and we need to import lumber for the wood. We need to bring in like graphite for the pencil lead. We need to bring in maybe like eraser type material, whatever. We're gonna bring it all to some central location in this factory, and we're gonna ship out a bunch of pencils. Okay, but maybe all these inputs have different type of transportation costs. Like for example, maybe the lumber is not shaped very well; it's all bulky, and we're also not going to use all of it. We're going to shave off a bunch, so we're like bringing in a bunch of mass that just ends up being thrown away. Right? So it's like a relatively large transportation cost versus the final packaged pencils. It's like, well, that's just the final mass can be like the smallest amount. There's these nice rectangle shaped boxes. Maybe that has a small transportation cost. It's just easy, right? Okay. So what would make sense? Put your factory closer to the lumber, or closer to the let's say the town where you're eventually shipping the pencils off to. If it's really expensive to transport the lumber and really cheap to transport the pencils, what do you guys think? Yeah. Let's put the factory like closer to the forest where we're getting the lumber, right? Okay. So you can actually solve this with a with the physics setup. So look, here's like a paper cutout of a factory. There's a bunch of strings tied together here. It's on a bunch of strings. And each of the strings is looped over. Ooh, it looks like a pulley, goes through a hole in the table. And look at these lab weights, Okay. Well, what if each lab weight is proportional to the transportation cost? What you can do then is you can swap out. Oh, all right. So there's a close up of the pulleys. Right? You can swap out these lab weights. Right. And if something was like say more expensive, right, then you could represent that with a larger lab weight. And you guys see the factory naturally shifting towards right, like, towards that particular resource. Yes, right. So the natural equilibrium point will tell you exactly where to put the factory. Then here's the map version of right. Slide around. All right, so my other classes are doing that. You can kind of see back on lab tables. We're constructing some this Veranon frames. Okay? At least you guys get to see that and get the concept. Okay. One more thing before we start on this Atwood FRQ. I was maybe ideally hoping there was going to be a little bit of time left over in class. I was going to sort of quiz you guys, see if you could get some of these posters from scratch. Like, here, we'll just do a quick run through here. Right? Like, if I asked you guys, could you come up with, for a classic Atwood, could you come up with the acceleration expression like from scratch? Could you do that? I showed you 2 ways to do it. Right? System equations here, or like from a system point of view. Right? Actually, your FRQ today is really similar to this one. So, could you guys suppose I was covering all this up and I asked you guys, can you determine what's the rate the car can slow down, the acceleration of the car, maybe negative acceleration, right? How fast can it slow down? Right? Could you guys from scratch figure out that'd be this right here? And you guys remember the mass of the car cancels out? It's always a classic physics question, right? Take physics in college, you're for sure going to see this question. They're going to say, what happens if you double the mass of the car? You say, oh, it has the exact same motion. It's not cancel out. Could you guys draw that like from scratch, right? Could you guys take that and tell me, suppose it was sliding down at constant velocity, which would be a type of equilibrium. Could you guys determine what is the coefficient of friction based on this angle? Right? Could you guys figure out all those steps and figure out, oh, well, it's the tangent of the angle, right? This should be something you should be able to do, right? Should be able to do, right? That could be an FRQ right there. Okay, let's figure that out. Okay. What if we get rid of the friction? Right. Could you guys say, suppose you have an air hockey table and you just tilt the air hockey table at some angle. Could you guys tell me how much it's accelerating? Because in this case, it would be accelerating, wouldn't it? Right. Ooh, wouldn't this here component be the net force? Right. Net force driving that mass. which then you just very simply divide the mass, right? That one's a lot simpler, right? Right. So, hey, when you guys were rolling your Hot Wheels cars down, they were accelerating, turns out that much.
Teachers, pardon the interruption. I have a couple of important announcements. First,
All right, record resume. Right, and finally, I got one more of these. Right, do you guys remember like elevator physics? If you're accelerating up or down in an elevator, it might feel really light or really heavy, right? Or maybe like equilibrium, right? Could you guys derive these expressions? I don't have the full derivation on here, but it's in your notes, probably, right? Right. Can you guys figure out tension in the elevator cable or force rating on the scale? It would be right, right, based on the acceleration of the elevator, or the other way around. Suppose you knew your scale rating, could you calculate what the acceleration of the elevator was going to be? Right. So yeah, you guys should be able, ideally, to have all those skills. We're kind of closing out this section, right? We're going to start a new topic on Monday. All right, let's switch over and do this FRQ.